Hi, in this lecture, we are going to look at regulation of body temperature. So we know that normal body temperature is about 37 degrees Celsius, or we say 98.6 Fahrenheit. We know that we need to maintain normal body temperature for many reasons, one of which is the enzymes. We know that enzymes have a limited temperature range. If you get it too hot, the enzyme can denature. Remember, enzymes are protein molecules, and when they denature, they change their shape, and then they don't work anymore. A good example of this is if you've ever cooked an egg. The egg white is a protein called albumin, and when you cook it, it's denatured. It completely changes, and it can't go back to normal. So we need to maintain body temperature. It's one of those things it's critical for homeostasis, and this process is called thermoregulation. So when we look at thermoregulation, we know we always produce heat as a byproduct of metabolism. When we eat our food and we use those nutrients to generate ATP, we lose about 40% of that as heat. Now, we also know we generate even more heat when we exercise any physical activity, as well as if our metabolism were to go up, we're going to produce more heat. A lot of this heat is retained by the water in the body. Having so much water is good because it prevents drastic temperature changes. However, if we generate a lot of heat, we have to have a way to get rid of it. So we have to have mechanisms to lose it to our environment. And on the other side of things, if we're too cold, we need a way to gain heat or to increase our body temperature. So we know that 37 degrees Celsius is our normal range, 98.6. We know as we get colder, it can cause problems with physiology. Things, basically slow down. If we get warmer, it tends to increase metabolic processes and chemical reactions. But again, if it gets too high, it can cause death. So we have concerns if it's too high or if it's too cold. Now, in a human adult, once we get to around 106, a lot of times you might start to have seizures or hallucinations because the temperature is just too high. You're more likely, by the way, to see fevers more than you're going to see the hypothermia. But we need mechanisms to try to control our body temperature because if it's too high, it can actually damage organs and the brain. So we have two places we look. We have our core temperature, which is our ventral body cavities, basically your cranial cavity, your thoracic cavity, abdominal, pelvic. And then we have our shell, which is our skin. So the blood is the transporter. The blood actually moves heat between the core and the shell. So if we're trying to conserve heat, so we are in a cold room or we go outside on a cold day, we want to keep the heat in our core. Those arterioles to our skin will vasoconstrict to decrease blood flow to the skin. Because if the blood flows to the skin, we're going to lose heat from our body. On the other hand, if we're warmer, if we're in a warm environment, now we want to lose heat from our bodies, so those blood vessels will vasodilate. In this picture, you can see room temperature. 20 degrees is typical room temperature. You see a very cold room and a very warm room. And notice the temperature. We have the core temp. Look in a cold room. Notice we maintain the core temp for our brains and our hearts. And then we actually vasoconstrict to our extremities. In fact, our extremities, the temperature in our skin can actually drop to the environmental temperature because of that vasoconstriction. Here's our normal room, and then when we're very, very warm, we vasodilate, so we really try to send all that blood to the surface so we can get rid of that heat. So when we look at, regulation, thermoregulation, you're basically going to make sure that you're producing heat, your metabolism. If we're very, very cold, muscle activity, shivering, thyroxine, metabolic hormones. So we make heat, and then we have mechanisms of heat loss. So these are the four ways that we get rid of heat from our body: radiation, conduction and convection, and something called evaporation. So if we look at these processes, radiation is literally the loss of heat off of our bodies as infrared radiation. And so we radiate it off of ourselves. it's off our body and off our skin. Now, other surfaces radiate heat, by the way. If you've ever gone outside on like a hot summer evening, you might see the heat radiating off the pavement. And so it's just infrared waves. There's infrared cameras you can use, right, that at night to try to look for living objects, because if you're alive, you're going to radiate some heat, so they can find you with infrared. And we lose about 50% of our heat this way. This is why if you're in a crowded room, the room heats up as people are in that room, because everyone's radiating some heat off of them. Now, conduction is through direct contact. So the surfaces have to touch. So if you're sitting on a chair, if you were to reach down and touch the seat of your chair, it'll be warm because you conducted heat from your body into that chair through conduction. Convection relies on air currents. So basically, we know that if air is circulating, as we lose heat to our surrounding area, if there's flow of air, as the air comes in, the air comes near our body, it picks up the heat and it rises and it's replaced by cooler air. This is why a fan, anything that increases circulation, is going to help cool you off. So if you're very, very warm and you don't have a fan, maybe you get some paper, right? And you fan yourself and it cools you off, because when I'm doing this airflow is picking up the heat off my body and moving it away from me. Now, on a very cold day, that can backfire. We have what's called the wind chill. So if you go outside on a very, very cold day and it's windy, you're going to be cool really, really fast, right? You're going to cool off much faster than typical. So they might say it's, I don't know, 16 degrees out, but with the wind chill, it feels like -2. And then evaporation is the last way we have to kind of get rid of heat. And this involves sweat. So as sweat evaporates off our body, it releases a lot of heat with it. So whenever we have evaporation, though, you have to have a low humidity area. So typically for sweating and evaporation to work, you want your humidity to be about 60% or less. Humidity is the amount of water vapor in the air. So, in Maryland, every summer, it's never below 60% humidity. I swear it's like 100% all the time. So you still sweat, but it doesn't cool you off. So you're just covered in sweat and you're taking 4 showers a day. As far as controlling heat gain and heat loss centers, we have these 2 centers that are going to be located in the hypothalamus, and just what their names say, you can see that we look at our 2 centers. So hypothalamus is the center for this. Think of the hypothalamus as the thermostat. So in this case, we have body temperature starts to go up. So the thermoreceptor is going to pick up increased temp, right? Thermoreceptors, sends it up to the control center and the hypothalamus, and it's going to help you lose heat. So you're going to vasodilate, so you can send the heat to your skin, and then you can lose it through radiation, conduction, convection, and then it will also make you sweat through evaporation. So once you're sweating, that's like the last resort. That's your body's last chance to cool you off. Now, on the other hand, if we were to have our body temperature falls, so now it's colder, our thermoreceptors pick up that it's colder, they go to the hypothalamus, and now we're going to try to generate heat. So our blood vessels constrict, we're going to start to shiver, and we might even release more thyroid hormone. So remember, when we're looking at the body temperature, a lot of times what we're looking at are these blood vessels. And so these vessels can either vasodilate and increase blood flow to the skin in a warm area, or they vasoconstrict when we're too cold to keep the heat towards our core. So if we look at the details, if we look at the heat gain center, this is what happens when it's cold out. So the first thing is we're going to vasoconstrict the blood vessels. We're going to decrease blood flow to our skin. So our sympathetic nervous system is involved. We're going to be having norepinephrine, because norepinephrine is going to vasoconstrict. We're going to decrease blood flow to the skin. Now, when this happens, our shell temperature will fall. And you have to be careful, because technically it would fall until equilibrium was reached. because heat, like anything else, flows down a gradient. So this is when frostbite can occur. So if you're outside on a very, very cold day, you will vasoconstrict, and if you're not protected, your skin temp will drop to the environmental temperature, and if it's too cold, it will actually freeze your skin. Your skin will die, and some of your tissues as well. We can also increase metabolism. Norepinephrine is involved with this too. If we increase our metabolic rate, then we're going to produce more heat. If that doesn't do it, we're going to start to shiver. So we know shivering are involuntary contractions of skeletal muscle. It's done to generate more heat. And then in colder climates, you might see an increase in thyroxine. Remember, this is the hormone T4 from the thyroid gland. So maybe if you live in like Maine or New England and you have very long winters, in those people, they actually make more thyroxine so that they can generate more heat. Because remember, if your metabolic rate goes up, you generate more heat. Now, what if you're too warm? Well, if your body temperature is too warm, we said you're going to vasodilate. We're going to send the heat to the surface. This way we can get rid of heat loss through radiation, radiated off our bodies, conduction, direct contact, and convection. If that doesn't cool us down, then we start to sweat. And we said evaporation is very good at releasing heat, but we need to have a low humidity environment. So roughly less than 60%, because that's what allows you to lose the heat when you sweat. Otherwise, you still sweat, but you're not releasing heat. And that's why there's those special fabrics now, and the Under Armour has these heat fabrics. And what they do is they actually help wick away the sweat so that you can release more heat. If you're just wearing cotton, the cotton just absorbs the water. It doesn't do anything to help you dissipate the heat. Now, these centers work really well in adults, but with infants, not so well. For one thing, they're not developed. When we look at infants, they don't really regulate as well. They lose heat really, really fast, and their body temperatures are all over the place. So their metabolic rates can drop quite a bit when they sleep and rise after waking. They can spike fevers, temperatures can fall. Infants can't shiver, but they do have something called brown fat, which is a very metabolically active fat. And what that fat does is it generates a lot of heat for the baby. Now, some disorders, if we have hyperthermia, excessive heat, there's something called heat exhaustion and then heat stroke. So let's say you're outside on a hot day and you're getting dehydrated because you're sweating so much trying to cool yourself off. Well, when we look at heat exhaustion, that's what sets in first. So typically you're dehydrated, you're going to be sweating a lot, your skin might be cool, it's going to be clammy from the sweat, you might feel like you're going to throw up. Your heart rate may go up and you usually feel lightheaded or dizzy. You can even get muscle cramps because you're so dehydrated. So when this starts to set in, it's important to get out of the heat, drink water, get fluids in you. If you've been sweating for over an hour, you probably need some Gatorade or some electrolytes as well, and then you can cool yourself off. Now, if you don't heed those warnings and you stay in the heat, you can rapidly progress to something called heat stroke. And heat stroke is a medical emergency. The issue with heat stroke is, in heat exhaustion, you're still using negative feedback. You're still trying to cool down. In heat stroke, the body temperature is so high that it actually causes the hypothalamus to stop trying to cool you off. You go into a positive feedback. And the classic sign is dry skin, red hot dry skin, because you stop sweating. Your body stopped trying to cool you off. As we get hot, this goes very, very hot, very, very fast. It will damage organs. We talked about the brain. It can cause seizures. You can lose consciousness. It does affect organs. There's heat shock proteins that damage organs. And unfortunately, this can be fatal. And you hear about people passing away in, the summers, often from heat stroke. Now, hyperthermia is our controlled fever, which we've talked about in the immune system. So the pyrogens are released, usually from the macrophage or white blood cell, and that changes the hypothalamus. Remember, the hypothalamus just resets itself. So the hypothalamus raises your body temperature to a higher temperature so that you can, fight the infection. And a lot of times prostaglandins can do it. These are hormone-like chemicals. There's one called PGE, but the prostaglandins reset. So now when your body's trying to generate a fever, you're going to vasoconstrict blood vessels to your skin. So your skin is going to cool off. You're going to feel very, very cold because now 98.6 is too cold for you. So you'll feel cold. You'll feel very cool. Your temperature will go up. You'll probably start shaking and shivering because your body's trying to generate heat to bring your temperature up. The fever we know is good. We know that it helps fight bacteria and pathogens, that it helps our white cells. It increases the rate of all the chemical reactions we need for our defenses. So as far as treat or not treat a fever, that's pretty much up to you. We do worry if the fever gets too high. We worry about dehydration happening, and we talked about concerns with organs. So real quick before I show you that slide, just know that when we get past the infection and our body temperature needs to return to normal, now we're going to do our heat loss mechanisms. So now we're going to vasodilate. So you might look flushed, you might start to sweat because you're trying to eliminate that heat. And if you've ever had like the flu or a cold or been sick, at night, or maybe you start to feel really, really cold and you grab all the blankets and maybe you take your Tylenol, and then an hour later you're sweating and you're kicking all the blankets off. And then when it wears off and your fever's spiking again, you're getting really, really cold, and that's the cycle of a fever. So remember, if our body temperature is too high, it's not going to be good because, we can start to cook our enzymes. Our proteins don't work as well. So the hemoglobin molecule, it won't be able to transport oxygen as well. We can damage our brain, we can damage our heart, and it can be fatal as our temperature climbs higher and higher. So we don't want to let a fever climb too high. We want to make sure that we're able to keep that temperature down and prevent those concerns. Now, what if it gets too low? Well, hypothermia, everything slows down. So you can see as we start to get colder that, it's not very comfortable if you've ever been really cold, right? You start to shiver really bad. It can make you start to get sleepy. You will lose coordination. Once you get too cold and the shivering stops, you basically go unconscious, and then your heart stops. So we know that when we have hypothermia, it slows everything down. Cells, tissues, organs are going to be less active. And then as it gets too cold, the heart will stop. Well, knowing that hypothermia slows everything down has actually been used as a treatment. So if somebody should have cardiac arrest, then what happens is obviously their heart stopped beating. Well, we know CPR is critical, and CPR is attempted, and it does help a lot. But what they found that really helps with the prognosis is to cool the patient. So they can put these cooling pads on, and they basically put them into hypothermia. They induce it, because when you're induced, then your cells don't need as much oxygen because the metabolism is slower. So they don't need to make as much ATP. Your neurons slow down. Your neurons don't need as much oxygen. And so this induced hypothermia has been really helpful in allowing people to survive concerns with cardiac arrest. You may have heard if someone has a drowning in cold water versus warm water, if they're submerged in cold water, they're more likely to survive than warm water because it basically decreases their cells' need for oxygen. So this wraps up our lecture on body temperature.